Okay, we need to confirm audio and video availability. Able to hear from them. Sir, can you say something when you want to test the audio?
dt by dx in the interface can be approximated by this variance. But you have to work with that.
We have an issue with that. We did not get some correct.
What?
If dt by dx is a variation and you have t naught there, how can t star be t naught? Because you have a constant slope. You have a non-zero slope.
This is not a constant slope.
Non-zero slope. You have t naught and you have non-zero slope.
This slope is 0 here,
Ah.
and its slope is changing.
Then if the slope, there is a slope, how can t star be t naught?
T star is here.
This
is 0. Asymptotically, this is 0.
T star is on the line with zero slope.
But you're integrating 1 minus h of I. When you integrate 1 minus h of I, you're not. This is inside the integral.
No, dt by dx is outside there. This is outside. This is the slope itself.
Oh, it becomes outside. Oh, it's coming out.
dt by dx
Going
is
to be
outside integration.
Yes. No. Now we will substitute the.
This is dt by dx is this.
Yes. Dt by dx is 1 minus h of I.
1 minus h of I, yes. So dt by dx at the solid is 0.
But when you come from 1 to 0.5.
Here it is 1, no?
Yes.
Here is 0.
0.
dt by dx at 1 is 0.
Yes.
dt by dx at 0 is minus h by k.
Yes. So what is the dt by dx at 0.9?
9. I'm talking about 1, 0.
That is fine.
0 is minus h by k. Here it is 0.
Yes.
What I'm doing is I'm drawing an asymptote from 0, which is a flat line because the dt by dx is 0. Here. dt by dx here is not 0.
Yes.
So when I draw a line here, it will go somewhere.
Yes.
I am denoting this temperature as T star.
Yes.
And this T star and this value is what I'm trying to compare.
Okay.
And if the value is in the functional variation of dt by dx is this, yesterday what we proved is that T star is equal to T.
So if we take the slopes at the ends,
Yes.
they merge at T star equal to T naught.
Yes.
But in the next formulation, there is an integral and a 1 minus h of I is inside the integral.
1 minus h of I, integral of 1 minus h of I has certain properties which leads to that thing. That's what we proved yesterday. So now, when you do differential evolution, if we integrate this one more time, you have LB over K, integral of minus infinity to x.
This way. He has not started to teach.
This is what we have.
Now when we change.
This is the integral. I'm not going to, this is just thing.
Yes.
Okay. Now,
Can you turn on the mic? It's not.
here.
This is a very long wire. We'll put it there.
Hello.
This one we can put there. No, this is a very long wire. No, this has to be connected to the laptop. We can't.
So this is the temperature of it at any given point in the
Laptop. This is only one external button. the recording starting. How we can edit later.
Okay, so this is where we and the thing that we can derive the temperature at any point in the domain using this experiment.
Yes, yes. Oh,
Now,
let's see it from here.
so what if you want to now integrate from get the TL over here. This is if I mark it as TL. This is essentially P0 plus.
It's not visible to me also. Yeah. Turn on video. This is the video now.
Okay, this is TL. And then once I know TL, I also know this line of the slope. Right? So now compute P star. Will be TL minus W by 2 into the interface risk times the slope, which is right. dt by dx at h of t is equal to 1 or 0. We have made a sign error.
One message.
That is 1 minus h of.
Which is 1 minus h of pi?
Minus LV.
Minus LV by K.
Minus LV by K, 1 minus h of.
1 minus h of pi.
So we'll make plus LV by K.
Here it is minus 1.
No. dt by dx is equal to minus LV by K, 1 minus h of.
Right.
There are 6.
So, okay, this is what we had. So your T star will be equal to TL plus okay, and TL so you want to replace this with TL here. So you get not minus LV over K. Plus right. This is what we and here we started doing the like algebraic breakdowns. W we expressed as dx by dt times dt, right? Minus infinity to plus infinity by 2. Or rather, we described as zero to 0.5 to 0. So we are going from the right? And what we are describing as W by 2. And if you do this consistently, then This is what we had. And we broke down this integral precisely as 1 to 0.5 plus or minus 0.5 to 1. And this integral we split up into 1 minus 5 plus 5. So 1 minus h of 5. So 0.5, 1 minus h of 5, 0.5 to 0 will cancel with 0.5.
It is maybe also possible because dx by d5 happens to be a even function around 0.5.
That it is, but that is not using.
No, because you're integrating the terms we are cancelling. We're cancelling the integral from 0.5 to 1 and 0 to 0.5.
No, I'm cancelling not here. Here I'm cancelling because here I'm cancelling because they are the same integral.
So in the next term, which is by area,
I'm cancelling there and converting it into 1 minus h by d5.
Okay.
And when I'm converting it to p integral or an x integral, 1
Okay.
minus h by dx.
Okay.
I of x is a odd function, thereby the area comes.
Okay. Everything
the use of the symmetry comes to the next step.
Okay.
Here it is just a
Same integral. Same integral. Okay.
So the result of this, I will not repeat that calculation one more time, is that P star is equal to and this is essentially the point of the method that if P star is equal to P naught, you essentially have that both the asymptotes are matched. Right? The point over here is that if what we wanted, however, is that dt by dx is what we wanted, because this value, and we wanted to introduce this into the Gravity-Force equation to get a condition for. I will guess this because this is something that all of you have.
Just a minute. The writing. I think it's there. That's fine.
We have it recorded. No?
We have it recorded. No. It's obstructing the perspective.
Oh, sorry.
Yeah, I don't know.
Okay, so what we have over here is that we have a dt by dx, and we go back to our steady state equation. So we have this. They will not worry about the interface terms, but we will worry about the driving force. Where the temperature is no longer continuous. Okay. However, so we integrate this by parts where we appreciate this term and integrate this. Yes.
Nice. First one is slightly less visible, but everything is.
And, sorry. Now, this value is at right when it is h of t is 0, so this out. On the left hand, it is not. And here is where we introduce the dt by dx. Here. Okay, this is what we had. And we will assume for the time being that this integral is something that we can compute. Okay. 1 minus h of t is of t. This we can compute. Is a positive integral or negative integral?
First.
So either look it from that side or this side doesn't really matter because h of phi 1 minus h of phi are symmetrical. So the integral can also be positive. So it is therefore a positive integral, and this is the integral we gain as p. So you will then take the left side. This integral we have already evaluated. This integral is what we had over here. It gives this. By 6. And then you bring that here. Okay, times this integral will be speed. Together, we have it over here. Will be an d by d. So we do this, we will have to get careful about signs, otherwise it's too overwhelming.
Hi.
Yeah, this integral will be actually negative in this particular thing, so you have to do a time inverter. Yes. Okay, so this is what you would get. This minus this is equal to L by Tm delta. And so your effective kinetic coefficient is going to be Tm over L times this, which is equal to Tm minus. And since velocity is proportional to this, can be taken out. This entire term, and it is a positive minus a negative, which allows you to choose W and K in a way that is determined. So essentially, this is what we did yesterday in terms of the asymptotics, where we described that once we change the picture from an infinitely thin interface to a finitely thick interface, it allows you two things. First, it allows you to get a condition where you can do vanishing beta calculations. These are typical conditions where you are doing experimental techniques. And plus, you should also ensure with certain prices of how you interpret your case, you can ensure that your far field limits of your temperature field are matching. There is no trapping of it. So it depends on the choice of how you interpolate the mobilities, particularly the mobilities of diffusivity in some sense, the diffusivity of heat and diffusivity of mass. So you need to be worried about that. And in the ideal case, when the K's are equal, it turns out that the dD by dx is precisely this, and everything was sort of matching. The temperature fields on both sides of the interface coincide at a given value, which is a solid value. So whichever direction you look, whether the solid or the liquid side, doesn't really matter. Now, that's all good for the case of heat. But as soon as you now want to do something with you typically have the situation that the diffusivity of the solid is much smaller than diffusivity. Okay, that gives rise to the situation that in an interface with this, if you have flux, the flux is able to escape more faster here, but less here because it is closer to the solid. So your effective mass diffusion is reduced on the solid side and enhanced on the liquid side. So necessarily, because of this, as the interface is transmitting, there is cellular partitioning that is also happening during this. But the cellular partitioning has to happen through the interface. And if the interfacial effective diffusivity is small, natural to expect that some subunit will get trapped in the interface. And depending on the speed that you move, this trapping will be more or less. Okay. Now, so the trapping is essentially a function of two things. First, the extent of the width of this interface, as well as the velocity at which you are translating. The faster you translate, the more the repartitioning that has to happen, the more the trapping will happen. Similarly, the wider the interface, the more the area pressure diffusion is limited, and therefore, more the trapping will happen. So your trapping is essentially going to be influenced by these two factors. So how do we take care of this? As I remarked yesterday, the trapping that typically happens in experiments at higher speeds is a physical one. It's a certain trapping effect. We typically don't want to get rid of it. Okay. However, you are essentially having trapping over here because of a diffuse interface width, which is much larger than the physical, right? And therefore, it's an artificial effect to that extent. So we need to correct for that because it's hard. So you are having trapping at speed, where in experiments we do not have. To make comparisons with realistic experiments, therefore we need to correct.
So is there any cutoff velocity where actually trapping occurs?
There is actually not a cutoff velocity. You always actually for any interface width in principle, you will have some trapping. It's just the extent of trapping that you will have and you are okay with.
So how do you decide that?
It's up to the person who is doing the simulation. So basically, if you are okay with an error of, let's say, 10-3 to what your solid composition should come out, and your interface width is in that range, you're okay with it. But for a person who is not happy with that, you will have to do a correction even for that. Okay, so it all depends upon what accuracy of simulation are you ready to settle.
But this error in composition is the equilibrium composition you're talking about.
So when you are growing, so your solid is growing, right? The solid, when it is growing and we are now talking steady state, the solid will essentially assume a constant composition. Okay. What is this composition that it settles down to given velocity? Typically, if the beta is 0, that composition will be something which is the equilibrium composition from the phase. Okay. Now, what happens is, if there is solute trapping, the composition, this derivation is no longer possible because your asymptotes from both sides are not really the same, so you can't write down an effective beta expression. So therefore, your solid composition essentially saturates to some value which is different from the equilibrium composition because of the solute trap. Because solute is getting trapped, your composition essentially will go up and will be higher than the equilibrium composition that you want. Okay, so this is what you want to find, right? What is the final solid composition that is established? So here is where, as we decided, we need the anti-trapping. So we keep some of these important integrals plus, besides that we keep the dt by dx, we keep the expression for beta, and the rest of the things we can get from. Okay. So as I said yesterday, we start over here and again have the condition to integrate by considering the cells. One, you have the situation that this is. So now, firstly, what we will do is we introduce the situation that A is not really uniform. A is times A of P plus A with but A is 0. Okay. We have a situation where A is 0. We will have a situation where A is 0. So if you put that condition over here, you have the situation that d by dx of KL into 1 is equal to LV and as we did in the previous case, we can integrate this once, where on the left hand side of the interface you have KL into 1 minus 1, so this will go to 0, and you will essentially be left with and this will be P minus 1 will be alright. This is what you will have. Now remember, if I use this interpolation function as the same as the interpolation function over here, I have a situation that dt by dx becomes just LB over K, the minus, right? Which is essentially a situation where dt by dx is the same. Now, obviously, this is something that you don't have in reality because the temperature on the solid side, as I said, is something which is constant. And suddenly in the interface, we have a straight line, which is matching with the. So necessarily, when you do the extrapolation of the temperature from the interface, from the solid side, and the temperature from the liquid side, you are going to have a different thing. This is a straight. This guy is going and joining here. So the effective composite temperature at the interface will have it. So essentially what it means is you look at the solution from the solid side and look at the solution from the liquid side far away because extrapolate remember is a function of us. Okay. That means if I think of removing the interface, but how do I remove the interface visually? I extrapolate what I see on the macroscopic bulks liquid and macroscopic bulk solid, and they whatever they mean or don't mean is essentially my solution. And if there is therefore the jump at the interface, I think the interface exists, which is P equal to 0.5, you are having a discontinuity of temperature at the interface. The continuity of temperature at the interface, or in some sense chemical potential at the interface, is typically referred to as a jump interface. Right? Typically, chemical potential temperature are continuous at the interface. That is a typical condition that you put when you integrate a foreign interface. Right? But here, because of the way that you have a situation that your A is not uniform and it is biased towards one side, you land up in a situation that you have a jump in the temperature, jump in the chemical potential. That is what you have to see in trapping. This is essentially what is related from heat trapping over here and solute trapping in this.
So if we get some experimentally the interface width,
Yes.
so we input that interface within the simulation.
Yes.
So whatever is happening is because of actually happening.
Yes.
We don't need to deal
So
with
the point is this: if you were to actually put in a physical interface width, about 10 power then interface widths in experiments are of that order, as strong as you know. That is very small. So you're already approaching the sharp interface limit, so you're closer to this picture. And in this picture, as you look over here, the jump even if you consider it small. But as soon as you make it this picture, the jump is to that. Okay? Depending on how far this difference, as I said, is. Right? So what we learn from this is, because of this factor, you essentially have a situation that if they don't match here, it will be the mismatch will be small, but that mismatch will be scaling with as soon as I make the thing large. Right? So it's a direct function of how wide your interface width is. Right? And as I said, how fast the interface. So the trick we are going to be doing to construct is, as I said, going to be an addition to the diffusive flux, because all of this is happening because there's a flux mismatch between the solid and the liquid. So I'm going to add a current to correct for what mistake I'm making in the radiation. Right? And I know where to go to. I know that if my dt by dx looks like this, I'm okay. This will give me the right degree. So I will correct my flux by adding a term here such that my d by dx changes from here. Okay, that's the strategy, right? So let's see what we can do. So let's add something to the just for argument's sake. So we put the minus and put this as the becoming plus. Right? So to this plus, you want to add something. To this plus, we will add something. So what should we add? We will add a term, which will, let's say, some constant factor. And we all agree that the thing has to be proportional to how fast you are moving, right? It has to be moving proportional to how fast. So velocity, instead of putting it as a velocity, it as dv spike. And you need to point it in the right direction. The flux, this doesn't have a direction, right? So you need to give a direction to the flux. So it has to be pointing in a direction which is normal to it. You cannot be giving arbitrary points. You have to give the direction typically normal to the flux. So we will give it normal. Okay. Now, normal to the flux, this gradient of T as we have written down, this is the gradient which is going like this, right? You're going from 1 to 0. So if you have to go in the direction of this, this gradient is actually negative. It will point reverse towards you. So we have to get minus. Okay. Okay. So if you put this together, you have this is the term we have added. Okay. And let's not forget our baby here, where it is. All right. Let's say we have added this term. What is the unknown here?
Alpha.
I have left the certain degree of freedom. I will design it such that I can get back pay. Okay? That's what I also. Okay. So, by the way, this is not in the moving frame. So let's convert this into moving frame first because there's a time derivative. Okay. So, and in the 1D space, graph P is minus dt by dx in this case, so dt by dx. So the term that will come, finally, I will rewrite this term. Plus V alpha. What are we doing? Okay, this is what you will get. All right. Okay, so then the problem is rather trivial because I will just repeat what we did. We ignore this fellow, small, and we integrate once. Okay. So integrate from left side to the right. Okay. So if we integrate this once, right? Sorry, my mistake. As a d by dx here, don't forget the d by dx. This is coming from here.
Yes. Minimize that. Plus.
divided by dx. Remember, I have already, so let's write this way. This will already be 1 minus h of phi because the left side is 0. And d pi by dx on the left side is 0, so you will directly this minus the okay, job is done. Job is done. We pause. So let's take it to the right side. All right, which is all right. So what is your? Can somebody derive what alpha of p has to be so that it matches this?
We can just compare the second terms and substitute.
You already have one.
Uh-huh.
You have one sitting over there. What is the by dx, your friend?
The root of w by k.
Your friend is there. So if we're making matters our life a little bit simple, use h of p equal to p. You can do it even without h of p equal to p, but let's say h of p is equal to p. That makes our life slightly simple. So can we do that? H of p is p. dp by dx is so what is alpha of p?
K by omega.
Huh?
P is getting cancelled.
What?
1 minus p and the 1 minus p.
1 minus p and 1 minus p will get cancelled. Okay, very good. What do you are left with? Remember, if h of p is p, you need to go only to 1 minus p here.
L root of k by omega, no?
Huh?
L root of k
L
by
by
omega.
L by
Can we? Yeah, come on, guys. Alpha of p. This is a simple algebra.
L root of k by omega. L root of k by omega.
Okay, it needs to have L, right? L by k, k is already there. L
K will get cancelled.
will which k?
K has to.
K is already there, no? This k.
You took minus every with a
This k is already there. So L is also, so alpha will contain L.
Only L, not k.
L.
Okay, L.
L under root k by omega.
Huh?
L under root k by omega.
L
Under root k by omega.
root k by omega. Okay.
Done.
That is all?
Yes. Since we took h of I is 5, it gets cancelled. And KL gets cancelled.
So L root of 5 K by omega. You have that.
V and V by K we have on both sides.
V by PL.
So it's gone.
So you essentially confirm that if you put this expression over here, L K by L 1 minus P. So you will get total V d by dx is equal to will you get this? You get this, right? So what is alpha of P? So what is the anti-current current then? Okay. Alpha of P and all of you by G times dt by dt times that's all it is. Okay. Where's K? K is not coming, right?
Root. Oh no, the capital K is not coming.
Okay. And is not required. Doesn't require. For a function of. Just a function of L.
H of I is 5, the anti-trap current is constant.
Huh?
H of I is 5, the anti-trap current is a constant.
H of phi, yeah. H of phi is for H of phi. For H of phi not equal to phi, you will get a weighting. Is that okay? Does that make sense?
So I have a question. So during alloy solidification, so with the progress of solidification, so the fraction of solid is increasing. So you have solute rejection is getting more in the liquid.
Yes.
So this solute trapping will be more increasing in the interface, or is the
Solid trapping actually doesn't disturb anything with respect to what is happening in the bulk. It only modifies what is happening in the equilibrium. So if your particle composition is changing, effectively what is happening is the equilibrium will change.
yes.
The equilibrium will change, so everything with respect to bulk thermodynamics will remain the same. In the interface, which will correct for the equilibrium.
Yes. So the equilibrium is also changing because of this. So it will also change, right? Over the time. This anti-trapping current will also automatically be adjusted.
So typically in this particular case, it's just delta K. For the alloy case, it will be delta C, as you saw in the equation where we derived L, and that is delta C, C L minus CS, and CL minus CS changes.
Yes.
So you put CL minus CS over here, and take care of it. Right? That's as simple as it gets. Okay, so the concept essentially started from, you see, you notice something in the by deriving of the electrical limit. You have noticed that if this is the property of diffusion dt by dx in the particle, if it is having this, you naturally get a nice thing that the asymptotes from both sides match, right? And if they stop matching when this property goes away, what happens when the K is one-sided or there is a asymmetry with it. So you're correct for it in the one-sided case, because in the one-sided case, it is a well-controlled function of this type. So you can essentially integrate this the same way. If I have the final value of the dt by dx, like this, you can derive this. And once you can derive the dt by dx and the interface in the one-sided case, you know the correction that is required to go here. So basically, you adequately modify the flux in the interface in a way that you return back the correction required to go here. Right? So you introduce a degree of freedom, which is alpha of P, such that you get this ST. And for the very simple function as we noted, you just get a constant term over here in the correction. So, given this is so, if I now give you the alloy certification, can you quickly write down what the correction will be? Now that we have taken the analogous root of everything,
Composition.
for the composition field,
We'll make L delta C.
Sir, by the way, what is the sign of the flux? I mean, is it consistent with what we have said?
it will be the same. So it is the direction, it's a positive flux in this direction. So you will drive a positive flux in here.
The sign will depend on the grad field, the sign of grad field.
The grad field will decide the sign of. So if the interface is like this, it will flow this way. If it is this way, it will flow outwards. Very good. So in principle, can I give it to you to figure out what the composition will be? It's very simple because your starting point will be here. Okay, your starting point will be here. So phase field equation in principle can remain the same. All that will change in the phase field equation is essentially this term, which is going to be so this is why the asymptotics also become very same if we adopt the nice scan potential approximation, because all of it is just flowing from, you just need a change of variable in the asymptotics. From P changes to mu, so the nature of the equation will be the same. So basically, this is L, and you will have dVc by d mu over here, replacing M, which is K in the previous equation. So only the equation in the beta will change to dVc by d mu. But effectively, what will come over here, replacing this. This, by the way, is interface width. Okay, so your J is proportional to the interface width times dP by dt, which is proportional to velocity. The two terms we agreed influence the end circuit, right? So if you want to write down for the alloy case, I can actually immediately write down it is going to be CL minus ES to the function of mu times root of K by W times dP by dt. Just pulling my eye and writing down without doing anything. All right, this is essentially what we're getting. Right? Because of the similarity with respect to the equation, you don't need to repeat the same topics for an alloy or a pure material case differently, because the essential physics, as we said, is exactly the same, and just the change of variables, thereby the nature of the amplifier. Right? All right. Good. We have basically understood one of the most important and basic important and difficult concepts, phase field, and to that extent, we have made excellent progress. Right? Any questions?
From this, can you say anything about the temperature profile across the interface? Does it follow the h of like dt by dx?
It will exactly follow now. So because I did the correction, I am going here now. dt by dx will essentially go 0 here, 1 minus h by here.
But the temperature profile does not correspond to the T star equal to T naught asymptotic that we derived, right?
It will, because of this now. Because of this correction, now T star, which is the asymptotic value from the liquid, will exactly match T naught.
Asymptotic value T star is equal to T naught.
Yes.
But in actually the temperature profile.
Good question. Very good. So, for this to happen, the interface temperature is necessarily lower.
Yes. That is because dt by dx is positive.
No, the temperature has to be this. Which, if your asymptotes have to meet at the correct value, the interface has to go to a lower value in the interface. Mathematically. So otherwise can't happen. But that's not a problem. Because for me, the interface is a creation. I am basically worried about what my bulk solution, which is far away from the interface, is seeing at the interface. Asymptote. What if my asymptote is seeing the right value? My sharp interface description will
So
come
the asymptote value must be TM.
Or if beta is 0, it should be TM. If it is Li, it should be CL or CS. Equilibrium.
Okay.
So it depends on what you're talking.
It's the asymptote value. Not we don't care what's at the actual interface. The asymptote value must be the same.
Conveyed with sharp interface.
Yes.
But we have only taken that linear approximation, no? dt by dx.
If you're interested in the parabolic approximation, you go to the second order asymptotics. Higher, not second, this is only second order. You go to third order asymptotics.
And then that's still T star equal to 3 now.
You can still derive. So I have stopped at deriving dt by dx as 1 minus set of t. If I am interested, okay, I'm looking for the second term in the parabola, which is t squared. I can derive.
So it will give you a different like anti-driving curve. That's not what.
I mean, it depends on how thick your interface is.
Okay.
If your interface thickness becomes very large, where this profile doesn't follow this exactly, which will happen at large enough interface. Then you might have to write down high order approximation.
Okay.
Which is something that you can do.
Okay.
But typically, if you do that, but that equation will become a little bit more
Complicated.
automatically. Nothing stops you.
We can also impose a alpha dot on chemical potential. On chemical potential.
Alpha dot only.
Chemical potential. There is a chemical potential jump across the interface.
That's what we did, no?
No, we impose this for the. Okay, CS minus CL.
Yes, plus J, which is minus M like mu plus J.
Okay. 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 It depends on CS minus CL. Okay. Okay.
Yeah, so I didn't repeat it because exactly the same equation. You don't have to repeat it.
No. There's a concentration jump across the interface.
Which is the same
That is anyway. But
no, concentration jump is not a jump. Concentration will have a jump.
You will have a jump. But that will be perturbed by a non-zero beta.
So
no, why are we correcting it via mu and not directly in the concentration?
Because I'm writing a mu equation. And just because I was writing a p equation, I'm writing a mu equation.
Okay.
So the mu should not have a jump.
Okay.
But the mu should be continuous, and mu having a jump corresponds to the vector. So I'm correcting for the mu jump.
Okay.
C will have a jump.
But because mu has a jump, C will also have an extra jump.
But there's nothing called extra jump.
Okay.
So all you have is that this is your typical concentration profile. If the concentration profile here, CS, is not this equilibrium value, but starts to deviate. It takes a value which is slightly different. That's the trapping you are talking about. Okay. And that, so this starts approaching this way. Okay, so that's actually.
So that we can correct in the C field itself, right?
See, the point is this. I can write an equation for C for a function of mu. Alright, it's the same. It's the same.
Okay.
The what correction you will get is not going to be different.
Okay.
Okay. It's still going to be a flux that you add here to the diffusion flux.
Okay.
And the final shape of the equation that the J will take will exactly be the same if you start from a C equation or the mu equation.
Okay.
But you must write the right model. If you write the WBM model, there's a problem.
Okay.
In the WBM model, inherently, there are other effects that are coming in, which will not be allowing you to take because the structure of the interface itself is a function of the sum of the effects.
Okay.
You cannot take, whenever you do all of this, it will not be one single expression. Every time you change the sum of the effects, the equilibrium will change.